Okay, let's talk a little bit about the assumptions of linear programming. In a little bit, I'll show you how to solve linear programs larger than two variables where we can't draw them graphically. And that will involve entering these linear programs into computers and then press and solve. The issue is that once we enter the linear program into a computer, all the context of the problem is thrown out, right? To the computer, the linear program is just the decision variables and the constraints and the objective. It doesn't know about any real world connection between those variables, and it doesn't know any of the context. And so context is important. And so let's talk a little bit about the assumptions of linear programming. Your solutions that you get are only valid in the sense that your linear program or your context meets these four assumptions. So the first assumption is proportionality. Each decision variable contributes to both the objective and the constraints proportional to its value. What does this mean? Well, let's actually talk about the first two together. The second one being additivity, in that the contribution of each decision variable adds together both for the objective and then for the constraint. And these two together essentially tell us that we have linear functions for the objective and for the constraints. Okay, so those two together tell us that whatever we come up with for an objective function, it's got to be a linear function, and whatever we come up with for the constraints on the left-hand side has to be a linear function. But let's think about how this might play out in a practical problem. Proportionality, a common scenario where proportionality might be violated is when there's diminishing returns, where maybe the more of something you do, the less it contributes to the objective that you want. Okay, and so if you have those sort of diminishing returns, then you don't have a proportionality. The assumption is that as much as you increase your decision variable, as long as it stays in the feasible region, the contribution to the objective function should stay the same. Okay, and so anytime you have diminishing returns or something like that, or maybe the opposite of diminishing returns is accelerating returns, where something gets better and better the more of it you do, that would also violate proportionality. Okay. Additivity, the main way that this gets violated is when your decision variables interact with each other, where doing one and the other at increasing levels sort of changes the contribution to the objective or to the constraint. And essentially, so the additivity constraint is essentially saying that there's no synergy allowed between your variables. Where the sort of contribution of one variable is modified by the other variable. And so that doesn't work. I guess together, these also sort of rule out anything where you'd have any sort of nonlinear function of your variable being involved, such as the logarithm or a sine or any of the fun math functions other than linear functions are sort of prohibited by these two assumptions of linear programming. Of course, we break these assumptions all the time in practice where we're modeling something that isn't perfectly linear. And so when we break these assumptions, then we have to either think about, well, how valid is it? Is it just a small transgression or is it a large transgression? How much does that sort of mismatch between our theoretical problem and reality? How much of a mismatch is that? Is it an acceptable amount of error in our model? Because all of our models are wrong to some extent. Or do we have to use a different technique? And so there are other techniques where we do, for example, allow interaction between the variables. And so we can get into quadratic programming or other nonlinear objective functions. So yeah, and then there's different techniques used to solve those. But linear programming works in a lot of cases. And so these are sort of two things that we need to make sure that it's linear. Divisibility. The basic assumption of a linear program is that we can assume any fractional value of our decision variables. And so in the last example we worked where we got 1.5 aluminum framed windows as our optimal value. Well, you really can't make 1.5, or maybe, I guess it's number of windows produced per day. And so maybe you can make 1.5 windows a day and then you stop work halfway through that window and pick up on production the next day. And so maybe that makes sense, but there's a lot of scenarios that actually violate this, where we really shouldn't allow fractional values. And so if it is violated, then the solution is to move to what's called integer programming, where we only allow whole numbers. And we will jump into integer programming a little bit later in the course. So powerful technique, and it's built off of linear programming. So we'll tackle it sort of once we built the structure of continuous linear programming before we get into integer linear programming. And then the last one is the one that usually we actually never have in truth, which is certainty, that we know for certain each parameter in the LP, right? This one is essentially pointing out to you that garbage in equals garbage out. And so if there is uncertainty, or the degree to which there is uncertainty, or that we are fudging or guessing at the values, has an influence on the output. Okay, and so if it turns out that the true value of the profit changes drastically, we should expect the optimal solutions to change. And later on, we'll do a little bit of what we did at the end of the last example. We'll sort of, the solution to not knowing for certain is to do sensitivity analysis, which is essentially what if analysis on what happens as I change the various parameters of the problem. And I should expect that as I change those parameters, either the feasible region changes, and so some solutions that were feasible before are no longer feasible, or the objective function changes, and so I might switch which solution ends up being the optimal solution. So those are the four conditions or assumptions of linear programming. I'll have to say that you can break any of these, but then you might not be dealing with linear programming anymore. And so there's techniques of what to do if each of these are violated. But while we're working in linear programming, it's worth thinking about how well a given problem satisfies each of these conditions. So let's actually do that right away. And so here's a problem. Pause the video to read through it. It has a auto manufacturer who wants to make luxury cars and trucks. And yeah, they want to advertise both on TV, both on comedy shows and football games, and they want to kind of maximize the bang for their buck on the revenue generated by those commercials. So give it a pause and think about how maybe each of those assumptions might be violated. Okay, so coming back, let's maybe jot down some of the problems. And then I'll maybe, after we put down the problems, then maybe we'll talk about what are some of the solutions. So, first problem, and maybe a big problem, is that if you're airing commercials and you're airing multiples of that commercial and you're airing some on comedy programs and some on football games, if your goal is to meet certain viewership goals, right? Let's see. Yeah, we want to reach 28 million high-income women and 24 million high-income men. That should say men instead of mean. Typo there. If that's our goal, there's a problem, which is that each time we air the commercial, some of those people are going to be the same people. And so we shouldn't expect that we get 7 million unique high-income women every time we air a comedy commercial. And we shouldn't expect that each of the football viewers are also unique. And so a big problem in this sort of setup, or the thought process here, is repeat viewers. And this will violate sort of both proportionality, in that the number of unique viewers is not proportional to the number of commercials that we air. Also, it would violate additivity, mostly because we might expect that there's some overlap between people who watch comedy and football. And so there's sort of repeat viewers across the different programming types. And so each football commercial, after you've started airing comedy commercials, only generates fewer unique viewers. So yeah, repeat viewers is a problem, at least as the scenario is set up. Another one is divisibility. We want to specify the number of commercials that they watch. If we go ahead and set it up and solve it, we might get a whole number of commercials, but chances are we won't. And so we definitely can't have half commercials or quarter commercials or fractional commercials. Now, maybe we could make a different commercial that is half the length and not a whole 1 minute commercial, but definitely probably wouldn't have proportional costs, right? The cost for a half-minute commercial is probably not half the cost of a whole 1 minute commercial. And so there's definitely going to be divisibility issues of wanting to specify a whole number of commercials. And then the third problem that, as I see it, is that we really do expect that there's going to be a varying number of viewers for each program. And so I have very little certainty in any of these numbers as far as viewership for each of those, because football game to football game, that's going to vary widely based off of who's playing who and kind of the timing of the game. And same thing with comedy, in that if you look at the numbers for any show viewership, those numbers go up and down by quite a bit. So this one would violate the sort of the certainty condition. And so we might, as we'll talk about next semester in decision analysis, we might have to think about this probabilistically and think about the distribution that we get of viewers for each of those time slots and think about it that way. Okay, some modifications. here are maybe some solutions to the problems that we laid out. First solution, it's to focus on not unique viewers, but on views instead of viewers. This is probably a proxy for what we really want, right? And we'd sort of go back to our bosses and say, well, we probably can't give you a good estimate of the number of viewers over the campaign, but we can tell you pretty accurately how many views we got in. And there's maybe ways to estimate those from various Nielsen ratings and stuff like that on how many people saw those commercials, right? Some of them might not be unique. And so we might want to just focus on maximizing views with the idea that, okay, repeat viewership maybe isn't a bad thing. It's fewer unique people that are seeing my commercial, but sometimes repetition is good, right? It's maybe not the first time that you see that luxury car commercial that gets you to buy it, but it's maybe the 10th time where now it's like, oh, I got to go buy that Lexus or whatever that luxury car is. Okay. We'd probably also switch this from a linear continuous program to an integer program where we would force that the solutions would have to be integers so that we are dealing with a whole number of commercials. And then there's not a ton we can do for the certainty one other than maybe make precise forecasts for each of those commercials based off of each of the games. And then our variables would, instead of being number of football commercials or number of comedy commercials, is yes or no, should I put my commercial on this program and have some estimate of what's the cost for putting it on that football game program, which might vary from football game to football game, as well as how many people do I expect to actually watch that. And so there might be some level of modifying or dealing with that certainty by having better forecasts. Okay, so sum up the video. We talked about the 4 assumptions and then looked at how those 4 assumptions might play out in a scenario where you want to perform linear programming.